Hello, Calc students. Today we're basically just going to be doing a review of previous concepts you've seen in Algebra 2 and kind of dive into the idea of conics, and then eventually we'll get to some ideas and how conics and what we're going to do with them in calculus, but really we're just going to reintroduce conics and basically equations of conics today. Okay, so what we're working with today are parabolas, ellipses, and hyperbolas, and those are all examples of conics because basically if you take a plane and you intersect a cone in one of the following ways, you will either make a parabola, a circle, an ellipse, or a hyperbola. And we're going to work on equations of those, writing equations of those things, so on and so forth. So really it's more algebra today than it is calculus. But then we will see how these conic sections can be incorporated in a calculus context, I guess. So this should be a C. Okay, so any conic section can be represented with a general second degree equation, which is ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. But you'll more commonly see them in their locus forms, which basically just means that it's just some equation that satisfies a geometric property. So we'll start with parabolas, and we'll start with the standard form of a parabola. Now, the most common form we've seen is just the form where we have a vertical axis, where the parabola is opening up or down. But we're also going to talk about parabolas that open left and right. Okay, so the standard form of the equation of a parabola with a vertex h and k and a directrix y equals k minus p is given by x minus h squared equals 4p times y minus k. Okay, now a directrix k minus p, really we just have this parabola here. And if you have a parabola, let's use one that opens up for example. You're going to have some vertex. If you remember, that's kind of like the center point. And then you're going to have some focus here. And then you're going to have a directrix down here. And just remember from your previous experiences that this directrix and this focus are equidistant from any point on that parabola. And that the focus and vertex both go through that axis of symmetry, that axis. Okay, so we have x minus h in parentheses squared equals 4 times p times, in parentheses, y minus k. That is going to be a parabola's equation if it has a vertical axis. If it has a vertical axis, like the one that we drew above. Okay, if there's a horizontal axis, it's going to look like this. It's going to be y minus k squared equals 4 times p times x minus h. And that is going to be if we have a horizontal axis. Okay, now the focus lies on the axis p units from the vertex. Okay, the coordinates of the focus are always, basically you start at that vertex and you add that distance of p. Okay, so you start at that vertex and you add that distance of p. So if you have a vertical axis, well, normally the center is going to be h comma k. Right? Now, if you have a vertical axis, meaning basically that the thing opens up and down, then your focus is going to have the same x value, but its y value is going to change. It's either going to go up or down, right? So it's going to be k plus that p value. And then if we have a horizontal axis, okay, well in this case, the x value is the one that's going to shift to the left or the right. So you take that p value, add it to the x value, or h. Okay, so just to reiterate, this would be if it's a vertical axis, or if you have a horizontal axis, it will be the bottom one. Okay, so what we want to do is we want to find the focus of a parabola, and I would encourage you to write those equations down if you don't have them already. But we want to find the focus of the parabola given by y equals negative 1/2 x squared minus x plus 1/2. So, well, our goal here is to get it into the standard form. We want it to be like x minus h squared equals 4p times y minus k, or the other one. But which one is it going to be? Is it going to be a vertical axis or a horizontal axis? And you should recognize that since there's a quadratic term up for this x, we should eventually get it into the form x minus h squared which means it's going to have a vertical axis. So our goal is to basically get x minus h squared equals 4p times y minus k. So we're going to have to do some algebraic manipulation to get it to that form before we identify the focus and things like that. So what we're going to do here is, well, first we have y equals negative 1/2 x squared minus x plus 1/2. We kind of want to get rid of those fractional parts. So let's just factor out a 1/2. This is the same as 1/2 times negative x squared. Well, you factor out a 1/2 from 1. That's like doing 1 divided by 1/2, or that's going to be 2. So negative x squared minus 2x. And then we have technically plus 1. Okay, now what we can also do is just get rid of that multiplying by 1/2. Just multiply everything by 2. So this is the same as 2y equals, well, if I take 2 times that, it's just going to be negative x squared minus 2x plus 1. So we've gotten rid of that fractional part. Our end goal, remember, is to get it into that standard form. So what we have to do here is basically, we're going to have to eventually do something called, well, we want it to be factorable, and we want our factored form to be a binomial squared. Okay, well, right now we have negative x squared minus 2x plus 1. Well, what we can do here is just rewrite it and group these terms. We're going to, basically in all these types of things, we're going to, in these conic section equations, when you're trying to get them into standard form, you're going to have to do a lot of completing the square. And we can do that, well, if we just rewrite this, this is the same as 2y equals 1. And then we're going to technically factor out a negative 1 here. So it's x squared plus 2x. And we are going to complete the square right here. Okay, so we have 2y equals 1 minus, and now we're going to complete the square. And remember, to complete the square, just do this very briefly, to complete the square, usually you have some quadratic term. It doesn't have to be an x, but we'll just use the variable x for our purposes. You have some quadratic term, and it should not have a coefficient. And then you have some coefficient in front of the linear term. And what you do is you take that linear term, you divide it by 2, and you square that value. And then you add that and subtract that value. So then add and subtract this. I'll kind of talk through that as we do it. So what we're going to do is we're still going to have, well, we have x squared plus 2x. Okay, but then to complete the square, remember, you take that coefficient of that linear term, you divide it by 2, and then you square that value. Well, 2 divided by 2 is 1, 1 squared is positive 1. So we're going to both add and subtract that value. And the reason you add and subtract that value is so you don't technically change the value of this equation, because adding 1 and subtracting 1, well, that's the same as adding 0. But what we're going to do here is we have just created something that is factorable, and in fact, it is a binomial. You can factor it into a binomial, into a perfect square binomial. Okay, and then what we do is, well, this negative 1, that's not going to have anything to do with our factoring, so we just move it to the other side. So this becomes 2y, and technically we have this coefficient, or we have this constant 1, and we're subtracting this negative 1. That's the same as doing 1, well, 1 minus negative 1 is the same as 1 plus 1, so we have 2y equals 2 minus, and we can factor this highlighted part. Well, what are the factors of 1 that have a sum of 2? And this is just a perfect square binomial. And we get x plus 1 squared. We've just factored that. So we're getting closer to this x minus h squared form. Basically, we just have to move everything to the other side, and do a little factor, and we're good. So move everything to the other side. This is the same as 2y minus 2 equals negative x plus 1 squared. Divide by that negative, and then I'm just going to rewrite it. So we get, well, we divide by that negative, we're left with x plus 1 squared, or x minus h squared, equals, then divide by that negative, we have negative 2y plus 2. Okay, and now we want this to be 4 times some value p times y minus k. So what we can do is just factor out a 2. We have x plus 1 squared equals negative 2. Factor out a negative 2. Negative 2 times y minus 1. And now we have it in the form we want. We can identify our values. We know that our h value, so this implies that our h value, since it's x minus h, the h is going to be -1. K is going to equal 1. And our p value is going to be, well, remember that this is technically 4 times p. Well, we're saying 4 times p is -2, which means, well, if we solve for that, I guess I can write that. 4 times p is -2 if you don't want to do this in your head. 4p equals -2. Well, that implies that p is going to equal -1/2 if you divide by 4 there. So p equals -1/2. And we want our focus. That's all we have to do here. So our focus is going to be, well, since we have a vertical axis, remember we have x minus h squared. This is going to open up or down. Since we have a vertical axis, our center is going to be that h value, which is -1. And then we're going to take our k value, which is 1, and we're going to add that p value. So it's going to be 1 plus -1/2. So we're going to get a focus of -1 and 1/2. And that is our focus. And that's all we have to do there. Okay, so we have some other examples. We'll cover those later. We're basically just going to work on the algebraic concept. So now we're going to move on to ellipses here. Okay, so we have the standard equation of an ellipse. And the standard equation of an ellipse with its center at hk, all of these conic sections are going to have a center at hk. And a major and minor axis lengths of 2a and 2b, where a is greater than b. That's a key concept here for this ellipse. Keep in mind a is greater than b. So if you go up to this picture, that a value is just that distance from the center. And that a value when we're working with an ellipse is always going to be its distance to its vertex. That's going to be the major axis. The a is always involved with the major axis. And then the b value is the minor axis. So keep that in mind if you're ever graphing an ellipse. The a value is always the major axis, or the longer one. This is going to be an a value. This is going to be an a value. And the reason that it's important to keep in mind that a is going to be greater than b is, one, for the graph, it's always going to be the longer axis, the major axis is going to involve that a, and it's also going to tell us whether it's a horizontal or vertical major axis. So if we have a major axis that's horizontal, we're going to have the standard form for an ellipse is x minus h squared over, I got to make sure I save myself enough room here, over a squared plus y minus k squared over b squared equals 1. Keep in mind this value on the right should always be 1 when it's in standard form, so you have to get it to that. And this is what you're going to have if your major axis is horizontal. Okay, now if you have a major axis that is vertical, okay, it's going to be the same equation essentially, except those a values and those b values are going to switch. So if the major axis is vertical, well then the a value is going to be underneath that y minus k term. So we're going to have x minus h squared over b squared plus y minus k squared over a squared. So when you're working with ellipse, if this helps you, whether it's going to be a major or a horizontal or vertical major axis, just keep in mind that a value goes under, if it's horizontal, it goes under the x value. If it's vertical, it goes under that y value. Okay. Now we're going to move to an example here where we're going to omit this one for now. And instead, we are going to do a problem where are we graphing? We're just going to find some certain values. So what we want to do instead here is I'm going to do a new problem. We want to find the center, the vertices, and foci of the ellipse. And then we have this equation. 4x squared plus y squared minus 8x plus 4y minus 8 equals 0. And I guess one thing I forgot to go over very briefly. We have this equation where we have c squared equals a squared minus b squared. And it kind of looks like a derivation of the Pythagorean theorem, but it's not. It's actually a pretty complicated way that this is derived. But when you're working with an ellipse, you can relate these two quantities. You might be thinking, well, where the heck does c come into play? Okay, and c is going to be used in eccentricity, and it's going to be used when we're talking about finding the focus of something, or finding the focus of an ellipse. And I guess later when we're finding the focus of a hyperbola as well. So that c value does come into play, and that's how it's related in an ellipse. It's c squared equals a squared minus b squared. All right, so we have this equation. And what we want to do is to get it into standard form, and that seems kind of complicated. So we're going to have to do some completing the square here. So what you want to do is move your quadratic in linear terms for each variable, kind of group them together. I'm going to rewrite this equation and do exactly that. And then get your constant terms on the other side. So I'm going to add this 8, and then I'm going to group everything together. So I have 4x squared. Well, the linear term that corresponds with that is negative 8x. And then I have, I'm going to erase this, save myself some room. I have 4x squared minus 8x, and then move the y terms together. Then I have plus y squared plus 4y, and that's all equal to positive 8. We want to look at these things individually and basically factor them and complete the square. That way we have some x minus h squared plus y minus k squared over something. Now what we want to do is make sure there's no coefficient in front of that quadratic term, so we can factor out a 4 in both of these terms. This is the same as 4 times x squared minus 2x plus, well, we don't need to factor anything out here, y squared plus 4y. And then we're going to complete the square for each of these things. So this is equal to 4 times x squared minus 2x, and then remember we're going to divide by that coefficient in the linear term, and then square that. So negative 2 divided by 2 is negative 1. Negative 1 squared is 1. So we're going to add and subtract that value in the parentheses, and we're going to do the same type of process here. So we have y squared plus 4y, and then you divide that linear term by 2 and square it. So 4 divided by 2 is 2. 2 squared is 4, so we're going to add and subtract 4 here. Okay, now really when we're completing the square, we're really only concerned with these terms to factor, these terms. And then we move all the other terms to the other side. So you want to be a little careful here. If we want to move this negative 1 to the other side, we can't just add 1 because technically we're taking 4 times that value. So really this is a value of negative 4 that we are then moving to the other side of the equation. So to get rid of that, we're going to add 4. And, well, we're not multiplying anything here. We just want to get rid of this negative 4. We're going to add 4 again. And then we will look at these things in yellow and see what they factor to. Well, x squared minus 2x plus 1, that's going to factor to x plus, and I still have this 4 out front. It's going to be x, not plus. It's going to be, well, what are the factors of 1 that have a sum of negative 2? The answer is negative 1. It's going to be 4 times x minus 1 squared plus, okay, I'm going to factor this other part in yellow, y squared plus 4y plus 4. That factors to y plus 2 squared. And that's equal to, now we're doing 8 plus 4 plus another 4. That gives me 16. And we're in the home stretch here. Remember that we want this term right here. We want that to be 1. And to get that to be 1, we just divide by 16, which works nicely for us because we are also getting rid of this 4. So if we divide everything by 16, this is the same as x minus 1 squared over, well, 4 divided by 16 is the same as 1 over 4. So we have x minus 1 squared over 4 plus y plus 2 squared over 16 equals 1. Now remember, our objective for this problem is to find the center, vertices, and foci of the ellipse. So we have a lot of things here. Basically, we want to identify our h and our k values. So we know, well, our h is going to be x minus h, so h is 1. K equals, well, y minus k, it's going to be negative 2. So we have our center. That's the easiest part. Our center is 1 and negative 2. Okay, now our vertices, this is the somewhat trickier part. Remember, you take your vertices and you take that center value, that 1 and -2, and then you move a distance of a. Now we have to ask ourselves our question, is this going to be horizontal? Is it going to be a horizontal major axis or a vertical major axis? And since the larger value is under that y term, the major axis is going to be vertical. So we know there's a vertical major axis. To make a rough sketch of what's going on, we're going to have some ellipse like this. We're going to have a vertical major axis. So it's going to look like this. And I always kind of draw a sketch because it helps me. Here's our center. Then our vertex is going to be a distance of a in both directions. A distance of a in both directions. Okay, so our vertice then is still going to have that same x value of 1, but then we're shifting, we have two vertices, remember, we're shifting a value of a. And our a, I guess I should write that up here, our a and our b value. Okay, well our a value, a squared is 16, which means a has to be 4. And b squared, and since it's, I guess let's go back, well, a squared is 16. Couldn't a also be -4? Remember that a technically represents a distance, so a is just going to be +4. Then our b value is going to be 2 because 2 squared is 4. So for our vertices, we're going to move a distance of a. Well, if I go 4 up, that's like adding 4. Okay, so -2 plus 4, well, that puts me at 1, 2 for one vertice, and then my other vertice is going to be 1, and then if I took -2 minus 4, I'd get -6. So here are our vertices, very poorly drawn over here. 1 and 2, 1 and -6. And then this, of course, would be 1, -2. So here's our poorly sketched ellipse so far. Now we want to find our foci. Okay, now that's where our c comes into play. So this is where we need the equation c squared equals, and for an ellipse, it's a squared minus b squared. Well, if we plug in our values, we know that c is going to be the square root of, well, a squared is just 4, and then b squared, or whoops, a squared is 16, and b squared is 4. So 16 minus 4, well, that's the square root of 12, which is just root 4 root 3, or 2 root 3. So our c value is 2 root 3. The reason that's important is because we want to find that focus, this part right here. And our focus is basically just a distance of c from that center. Okay, so if our center again is 1 and -2, we're just a distance of c, so we still have that same h value, 1, but now our y value is changing. We're moving c, a distance of c from that center. Okay, well, if I start at -2 and I guess we can just leave it like this. It's like -2 plus 2 root 3. And, well, if we move the other direction, if we subtracted it, that'd be the same as doing 1 and then -2 minus 2 root 3. If you want to approximate these as a decimal, go for it. You can also just leave it in an exact form like this. Okay, and that's kind of how you would do that one. I guess simultaneously, it's kind of how you would graph it. Basically, you just use these things, plot them, and then sketch as well as you can, kind of an oval shape here. So that's all that we need to do for this ellipse. Okay. Now for the last thing, we're going to work with hyperbolas. They're kind of like parabolas. Work with hyperbolas. And this looks like a mess, and it kind of is a lot going on here. Just remember, it's still going to have this center. It's going to have this center, this vertex, and a focus here. We have all these things that are related together. And we're going to have a major and minor axis. And I guess in this context, we're going to call them the transverse axis. The transverse axis, which is this larger part. This is the transverse axis in both of them. Okay. So what you want to do here, and actually, excuse me, I want to correct myself. Those were not the transverse axis is this part here. It's the part, or maybe I did have that right. It's the part that connects the part that connects these vertices here. Okay, so this would be an example of having a horizontal transverse axis. This is a vertical transverse axis. Okay, so we have the equation of a hyperbola. The standard form of the equation of a hyperbola with center at hk, that's going to be a common theme, is x minus h squared over a squared minus y minus k squared over b squared equals 1. This is going to be if you have a vertical transverse axis. I'm going to zoom in here so I don't take up so much space. This is a vertical transverse axis. We'll abbreviate that transverse axis. Okay, or now if you have a horizontal transverse axis, what's going to happen here? The a and b values stay the same. The numerators are basically what gets swapped around. So if you have a, excuse me, this is, goodness, I'm backwards. This is a horizontal transverse axis. We'll kind of summarize this in the end. Horizontal transverse axis, this next one's going to be a vertical transverse axis. And the vertical transverse axis you get if you do y minus k squared over a squared minus x minus h squared over b squared equals 1. Again, keep in mind that it's 1. Now, kind of when you're working with hyperbola, as a way to remember this is the horizontal transverse axis is going to occur when the x term is in front. You're going to have a vertical transverse axis when the y term is in front. So that kind of makes a little sense. That might help you organize these. And we're also going to have a way that we relate the c and the a and the b quantities. Okay, so for an ellipse, or excuse me, yeah, for an ellipse it was c squared equals a squared minus b squared. For hyperbola, those quantities are going to be c squared equals a squared plus b squared. Where again, that c is still being used to find the focus, and the a is still being used to find the vertex. So at least those commonalities exist between an ellipse and the hyperbola. So we'll write that down. The vertices are a units from the center. And the foci are c units from center. That is exactly like an ellipse. That's the same statement for an ellipse. The focus is c units from the center. The vertex is a units from the center. Okay, but the way you relate these quantities is different. Where c squared equals a squared plus b squared. Now the reason that's different is because in a hyperbola, the ellipse is going to be further, or excuse me, in a hyperbola, the focus is going to be further than the vertex. That's not true in an ellipse. If we go back up to our ellipse here, remember that our focus is closer than the vertex. Okay, but those a values still is the distance to the vertex, and the c value is still the distance to that focus. So we're going to use this. There's theorems for the asymptotes of a hyperbola. We'll write those quickly, but you don't need to really know those. Because what we're going to do is essentially draw this box by finding this point, this point, this point, and this point down here. And then once you do that, basically that box just creates your asymptotes just by drawing the diagonals of that box. Okay, but if you do need to write the equation, it'd be helpful to have that. Really, when you're graphing something, just draw the box and then kind of sketch the vertical asymptotes, making a diagonal. Okay, so for horizontal transverse axis, the equations of the asymptotes are as follows. Okay, for a vertical transverse axis, the equations of the asymptotes are y equals, there we go, y equals k plus, and in this case it's a over b times x minus h, and y equals k minus a over b times x minus h. So really the only difference between the horizontal and transverse axis when finding the asymptotes is that instead of doing b over a like you do in the horizontal, you're going to do a over b in the when you have a vertical transverse axis, if you need to know the explicit equation. Most of the time you're just going to kind of draw that rectangle by plotting those points. This is a distance of b, this is a distance of a. And then from that center point, draw the box and kind of draw the asymptotes, and then your hyperbola from there. Okay, we'll move on to 8 some other time. What I want to do is a different problem. Basically just another Algebra 2 type problem. So what we want to do is, in this example, we're going to use the asymptotes to sketch a hyperbola. So we want to sketch the graph of the hyperbola whose equation is 4x squared minus y squared equals 16. 4x squared minus y squared equals 16. Okay, so this one's not too bad. Basically, we want to get it into standard form, which means we want to get this to 1. Okay, and the way we get that to 1 is to just divide it by 16. So 4x squared minus y squared equals 16. Divide all that by 16. We're going to be left with x squared over 4 minus y squared over 16 equals 16 divided by 16 is 1. Now you don't see your h and your k value, which implies that, well, that's easy enough. Our center is going to be 0, 0. We don't see those h and the k value because they technically are just 0. So there's our center. That's easy enough to do. We have our center at 0, 0. Now we want to find our a, we want to find our b, and we want to plot some points here. Okay, now keep in mind that your a value is going to be underneath the left fraction. So a squared equals 4, well, a equals 2 then, and b equals 4. And I'm going to color code these. Let's do this let's do a in red. And let's do b in blue. Okay, so basically we just start at the center and we move an a distance of 2. Remember that a corresponds with the transverse axis. Well, what's our transverse axis going to be in this problem? Well, we have x squared over 4 minus y squared over 16 equals 1. And since we have a parabola, keep in mind that it's going to be whichever term comes first, basically the non-negative term, is going to determine the transverse axis. And since the non-negative term is x, we're going to have a horizontal transverse axis. Okay, which means we're going to be going this way. We have a horizontal transverse axis. So our parabola is going to look something like this. Okay, I'll actually leave that there for now. It's going to look something like this, which means that, well, our a value is going to go left and right. So we have an a value of 2. We have a distance of 2 from the center. So let's plot our points here for this rectangle. So we go 2 this way. We go 2 this way. And if we wanted to label them, this would be 0, positive 2. This would be, whoops, got that backwards. This would be a distance of 2, 0. This would be negative 2, 0. Okay. Our b value is going to go up, so we go 1, 2, 3, 4 this way, and 4 in the negative direction. We wanted to graph that would be 0, negative 4, and 0, positive 4 here. Okay, but really, we're just going to sketch our rectangle outline. And then from there, we can make our asymptotes. At this point, I'm going to erase our thing there. We can make our asymptotes. We don't need to know the explicit equation for that right now. Goodness, let's try this again. So our asymptote's going to look something like that. Something like this. If you want to be more specific, you can maybe even count the slope on this and just draw some lines for these asymptotes, but we don't need to get that specific. This is what our sketch is going to look. Basically, these asymptotes, our vertex is going to exist on that a distance. So here's our vertex. It goes through these 2 points. And we're basically bound by this box and these asymptotes. So our hyperbola is going to look like this. And that's how you do that. So basically, our task when we're doing these types of things, there's going to be a lot of completing the square to get things to look like the standard equation. And then just graphing values, finding your A and your B, using those in the center to plot various aspects of your ellipse, your hyperbola, whatever it is that you're working with there. Okay, that's all we're going to cover. Have a good day, everybody, and as always, stay safe out there.